section 10.3, there's only one example that's given to you. Okay, and the example is, it says the diagram shows part of a curve with equation y equals f of x. Okay, and they've defined f of x as x cubed plus 2x squared minus 5x minus 4. And it says the point A with the coordinate, so we've got point A with x coordinate P is a stationary point on the curve. The equation f of x equals 0 has a root alpha, so we've got a root alpha between 1.8 and 1.9. Okay, and it says explain why. So first part is explain why x naught equals p, okay, is not suitable to use as a first approximation to alpha when applying the Newton-Raphson method to f of x. Okay, now the reason for that is because at this stationary point the gradient is going to be 0, and we can't have 0 as our denominator there. Okay, I've explained this in the intro. So what we're going to say is that so x naught equals p is not suitable because it's a turning point and then explain that f dash p is going to be 0 and we cannot divide by 0 in the Newton-Raphson method. Okay, so that's the explanation for part A. Now part B says using x naught is equal to 2 as a first approximation to alpha. Now notice that this 2 is outside of this range, okay? And the reason for that is that if we start at x is 2, then the gradient at that point is going to get closer and closer to the root, okay? That also was explained in the intro video. So the starting point can be just outside of this range, or it could be as close to the root, you know, but obviously, like I said before, it shouldn't be too far away from it. So using 2 as a starting value or as a first approximation, apply the Newton-Raphson procedure twice, okay, to f of x to find a second approximation to alpha, giving your answer to 3 decimal places. So what we want to do is we want to work out x1. So x naught is 2 minus f of 2 divided by f dash of 2. And there's a really easy method on the calculator that you can use. I'm sure you are all aware of it, but I'll just repeat it. So starting value is 2, so I'm going to press 2. I'm going to click equals. That now becomes my answer. Then I will write down or type the Newton-Raphson formula in terms of answer. Okay, so I've got answer cubed. I'm just inputting this formula there. Plus 2 answer squared minus 5 answer minus 4. Denominator, I've got 3 answer squared plus 4 answer minus 5. And I press equals, and that gives me 1.86 recurring, and I need to apply this once more, so I'm just going to press equals button once more, and I will get 1.8558, and to 3 decimal places that is 1.856. Okay, and that is our x2 to 3 decimal places. Part C says by considering the change of sign in f of x over an approximate over an appropriate interval, show that your answer to part B is accurate to 3 decimal places. Okay, so what we want to do there is we want to substitute the upper and the lower bound and show that there is going to be a sign change. Okay, so we are going to input so we're looking at this 1.8555, which will be the lower bound. If we input this value into our function, I get minus 0.00348. That is a negative. And if I put the upper bound, which is 1.8565, if I substitute this into the function, I get 0.00928, and that is a positive. Okay, there's a mistake in the book here. There's many errors in the book. Or we can just say sign change shows that x is equal to 1.856, correct to 3 decimal places. Okay.